Velocity of centre of mass. This is an important concept. If we have those two objects we started with, they don't have to be connected, but we've got two objects. If both of them are not moving, and we've worked out the centre of mass is here, then what's the velocity of the centre of mass? It's obvious, it's 0. But what if one of the objects or both of the objects were moving? Then it would have a velocity. Now, there's a very important principle which says that when you have a system, an isolated system, then if this guy's moving and this guy's moving and they've got a centre of mass, isolated system means, that's my implied symbol, means no external force on the system. Then our principle says no matter what happens in that system, the centre of mass, or the velocity of the centre of mass, velocity of the centre of mass will remain constant. So if we've got this ball is velocity equals 0, but this ball velocity equals 2 meters per second, and it's heading towards our ball and it's going to hit, then the velocity of centre of mass is something we can calculate with this equation. We'll call it x with a v, velocity of centre of mass, is equal to m1 v1 plus m2 v2. Look familiar, right? All over m1 plus m2. So what you're actually seeing there, sorry, can't see it. What you're actually seeing there is you're saying the mass of the object times its velocity plus the mass of the object times its velocity, all divided by the combined masses, gives you the velocity of the centre of mass for the system. So in this case, this example here, this one's not moving. So mass 2 times velocity 2 becomes 0. Mass 1, so if this was like 4 kgs, mass 1, and this one was 4 kgs, alright, mass 1 times velocity 1, 4 times 2 is 8. So that becomes 8 plus 0, alright. Mass 1 plus mass 2 divided by becomes 8. 4 plus 4. So the velocity of centre of mass in this case is equal to 1 meter per second. And if we've measured our velocities to the right as positive, since this comes out positive, we can say the centre of mass of these two guys is moving with a velocity of 1 meter per second that way. Now the thing is, we could sit here and say, well, they were both 4 kgs, which is nice. So at the instant I was looking at this, if I said that they were 2 meters apart, then we know by symmetry that 1 meter in the middle is where the centre of mass is. But we now know that that centre of mass in the middle is moving at 1 meter per second. So that's the formula we use to calculate the centre of mass. Now, remember the principle. I could have a box with 100 of these little guys in it, all moving with different velocities, right? And sometimes smacking into each other. Now, in this case, it's two-dimensional. Don't worry about that for now. I may show you in class how to work out the two-dimensional ones, but it works just the same. These guys will all have masses, they all have velocities. If we add up all their masses times the velocities and divide by all their masses, then we're going to end up with a centre of mass velocity for the system. And that's not going to change no matter how much they smack into each other. The only time it's going to change is if there's an external force operating on the system. So when they smack into each other, they exchange momentums, right? But there's conservation of momentum. And what you'll notice about this formula for velocity of centre of mass, another way to look at it is to look at it as this m1 v1 plus m2 v2 m1 plus m2. That top part is just saying total momentum, or total P, divided by total mass. So it becomes quite an easy thing to work out if you remember it that way. So if the total momentum doesn't change, then the velocity to the centre of mass doesn't change. And the total momentum doesn't change if we've got conservation of momentum going on. And we have conservation of momentum going on if this is an isolated system with no external force operating on it.